So, good morning, my dear students. Welcome back to my electrochemistry class. Let me continue the class. Okay, last class I have mentioned about the variation of molar conductance with the dilution. Okay, and from the variation, we can see that we can classify electrolyte into two category, that is strong and weak electrolytes. Okay, so depending on the nature of the variation of molar conductivity with the dilution or the concentration. Okay, because of the two different fashion by which the conductance vary with the dilution, you can see that it is possible for us to classify electrolyte into two different categories. That is, one is strong electrolyte and other is weak electrolyte. The strong electrolytes are those electrolytes which have already high conductance even at the initial concentration, and their molar conductivity or equivalent conductivity increases gradually with the increase of dilution or decrease of concentration. Okay, and finally reaches a limiting value. Example of strong electrolyte are all strong acids. Okay, strong electrolytes. All strong acid. Example, all strong acids. You are familiar? That is HCl, HNO3, inorganic acid, all inorganic acids, SO4, and all strong bases like alkalis, KOH, NaOH, etc. And three, all salts. Example, KCl, NaCl, CuSO4. Okay, all salts comes under this category. The aqueous solution of all six electrolytes are acting as strong electrolyte, and I have reason why the variation is like is to be discussed with the help of the theories. I am not going to theory now. Just for the variation, I am saying there are two different types of variation of the molar conductivity with the dilution or with the concentration. That is, at a given concentration or dilution or concentration, that is those electrolytes which have a very high value molar conductivity initially, and there is a slow gradual increase in their molar conductance with the dilution or decrease in the concentration, and reaches a maximum limiting constant value at a infinite dilution, that is called lambda infinity or lambda 0 m. Okay, these are category of such a strong electrolyte, but there are certain other class of electrolytes in which their molar conductivity is low initially at initial concentration, and with the increase of dilution or with the decrease in the concentration, their conductivity increases rapidly. Okay, their conductivity increases rapidly with the increase of dilution or decrease of concentration, and we cannot say at what stage it will reach a limiting value. That is the situation. So that the lambda infinity or lambda 0 of such an electrolyte cannot be determined graphically, and there is other method for determining the lambda 0 or lambda infinity of such electrolyte. That are the weak electrolytes. Okay, those electrolytes whose conductance are generally low. Weak electrolytes. Conductance are low. Initially their conductance are low, and there is a sudden or rapid increase in their conductance with the increase of dilution or decrease of concentration, and it going on increases, and it never attained a maximum limiting value even at infinite dilution. Example are all weak acids, acid like organic acid, all organic acid, CH3, COH, benzoic acid, etc., formic acid, etc., and all weak bases like ammonium hydroxide, aluminium hydroxide, zinc hydroxide, etc. Okay, all these are example of, and our organic amine, aniline, C6H5NH2, then amine, RNH2. All these are example of weak bases. Okay, weak electrolyte. Because the reason why they behave so is it will be explained only by means of the available theory. So we have to go on to that theory. Okay. So next I am going to explain the behavior or the variation of the molar conductivity of the electrolytes. For that we have to discuss the first important further is the first theory. Okay, that is the primary theory of the electrolytic dissociation, the fundamental theory of the electrolytic dissociation, that is called Arrhenius theory. Arrhenius theory of electrolytic conductance. Okay, that is the primary or fundamental theory, Arrhenius theory. So I am going to discuss about the Arrhenius theory. Of electrolytic conductance. This is considered as the classical theory or the fundamental theory of the conductance behavior of electrolytes, all electrolytes in their aqueous solution. Okay, one by one we can discuss the theory. Okay, this is put forward by Arrhenius. Okay, this says that one, the postulates of the Arrhenius theory is that all the electrolytes in their aqueous solution get partially or fully or partially or almost fully dissociated into their ions. Okay, that's the first concept postulates of this theory. That is the molecule of the electrolytes, acid base and salt, they will dissociate in their solution, their aqueous solution, are dissociated into their ion or charged particles. Okay. So the molecule of the electrolyte get dissociated into the charged particle, into ions, charged particles in the solution. In the solution, usually the aqueous solution. In most cases we are dealing with aqueous solution. Okay, and there exists an equilibrium, between the undissociated part of the salt, that is electrolyte molecule, with the dissociated or free ions like this, Mx, dissociated partially or fully, almost like that, to M plus aqua plus X minus aqua. So there exists an equilibrium between, okay, Mx or AB, okay, anyway you will like this, there exists an equilibrium, AB, A plus aqua plus B minus aqua. So there exists an equilibrium between the ionized species or ions and the undissociated molecule of the electrolyte. So you can take this as one of the postulates, that is all the molecule of the electrolyte dissociated into their charged particle or ions in the solution, okay, almost partially or fully, and there exists an equilibrium between the undissociated molecule with its ion in the solution. Then, next is, under the influence of the electric field, we are applying a potential, so under the influence of the electric field, the ions are free to move, migrate towards opposite electrode. So under the influence of the electric field, the ions are free to move towards the opposite direction. Okay, that is called that migration gives rise to the conductivity, and the extent of the strength, the amount of the conductivity or the conductivity, the power of the conductivity depends on the number of the ions that are moving or migrating towards the electrode. Okay, assuming that for a given electrolyte, the speed of the free ion is a constant. That is a very important situation. So you have to remember that the ions are free to move. The ions are ions are free. The ions are free to move towards the opposite electrode, and the conductivity of the solution is due to the movement of the ion towards the opposite electrode. Okay, and at a given concentration, okay, 3. At a given concentration, okay, Arrhenius assumed that at a given concentration, the electrolytes molecules are not fully ionized. Okay, they may be partially ionized. Okay, so the fraction of the total number of molecules of the ions that undergone dissociation is called the degree of dissociation. So he introduced a concept called degree of dissociation alpha, which is defined as the fraction of the electrolyte, total amount of the electrolyte that have undergone dissociation. So the degree of dissociation alpha of an electrolyte is an important quantity in conductance, which is defined as the fraction of the total amount of the electrolytes that have undergone dissociation into free ions. So it is expressed in terms of a decimal or percentage. That is, alpha is equal to the number of free ions divided by the total amount of the electrolytes. It's a fraction. Okay, into 100 if it is a percentage degree. So the number of free ions divided by the total amount of the electrolyte gives with the degree of dissociation, and Arrhenius assumed that it is always a fraction because the electrolytes are only partially ionized in their solution. Okay, that is expressed in terms of the degree of dissociation, and he again says that the conductivity of an electrolyte in the solution is a function of the degree of dissociation. It's a function of the degree of dissociation, or it depends only on the number of ions present in the solution, assuming that the speed of the ion does not change in a given concentration of the solution or with respect to the concentration of solution. He made an assumption. Okay, again I am saying that this assumption is going to be changed later. But Arrhenius assumed that the conductance of an electrolyte in the solution is dependent only on the degree of the number of free ions present in the solution or on the degree of dissociation, assuming that the speed of the ion does not change with the concentration of the solution. Okay, it is his assumption. Okay, then next is the degree of dissociation, the effect of dilution or effect of concentration. That is the fourth assumption. So the second assumption is, under the influence of the electric field, the ions are free to move towards opposite electrode, that gives rise to the conductance, and the electric field has only a directional property to the migration of the ion, and this does not produce any free ions. So the electric field does not produce any ion. It gives only directional property to the movement of the ions of the solution. Okay, and the electrical conductivity of the electrolyte solution depends on the number of free ions present in the solution. That is explained by parameter called alpha. Okay, in terms of the parameter called alpha, that's the degree of dissociation, which is defined as the fraction of the total amount of the electrolyte that have undergone dissociation to free ions. That is the number of free ions divided by the total number of the electrolyte, which is always a quantity lesser than 1. Okay, so depending on this number of free ions, an electrolyte has a conducting power. The next, fourth thing is that effect dilution. As the solution, and again that is assuming that here also another that is addition point to be mentioned is that the speed of the ion in a given electrolyte, the speed of the ion for a given electrolyte does not vary with the concentration of the electrolyte. Okay, does not vary with the concentration of the electrolyte. It depends only on the conductance depends only on the number of free ion present in the solution, because speed of the ion is a constant for a given solution. It is assumption. The fourth assumption is that the effect of dilution. As the electrolyte is diluted more and more by adding more water, that is by decreasing the concentration, the process of adding more and more water to reduce the concentration of electrolyte, that process is called the dilution. That is called the dilution. So the increasing the dilution by adding more and more water so that the concentration of the solution diminishes. In that such cases, the more and more electrolyte get dissociated free ions so that the degree of dissociation increases. So the effect of increasing the dilution of the solution is to increase the degree of the dissociation of the electrolyte, thus producing more and more free ions in the solution, thereby increasing the molar conductivity of the solution. And he said that, assume that at the stage of infinite dilution, that is, the electrolyte almost fully dissociated into free ions, so that the complete dissociation of the ion occurs, so that the conductivity, molar conductivity reaches a maximum limiting value, and that is called lambda 0m or lambda infinity m. That is also very important. That is the fourth assumption, that is the effect of dilution. If the solution is diluted, electrolyte solution is diluted by adding more and more water so that its concentration is reduced, more and more electrolyte get dissociated into free ions, that means the degree of dissociation increases, thereby the conductor's molar conductivity increases. And finally, at the infinite dilution, the dissociation of the electrolyte get completed. At that stage, the conductivity reaches a limiting value, that is called lambda 0 m or lambda infinity m. Therefore, for fifth assumption is that is 5. And for the degree of dissociation is a very important quantity that will give you that is conductive power of an electrolyte in terms of this lambda. That is, if we know lambda 0 m, that is, if we know the limiting conductance of the electrolyte at the infinite dilution, and then knowing the conductance of the electrolyte at any other concentration, given concentration, then the ratio lambda 0 m by lambda cm, okay, lambda m, or lambda infinity m divided by lambda m is lambda cm, that gives nothing but the degree of the dissociation. So we can measure the degree of dissociation. We can experimentally measure the degree of dissociation of any electrolyte. According to Arrhenius, he says, the degree of dissociation of the electrolyte at any concentration alpha c is equal to its equivalent conductivity at a lambda c by lambda 0, I think. Okay, lambda c by lambda 0, alpha c is lambda c by lambda c m by lambda 0 m, or lambda c m by lambda infinity m. Sorry for the mistake. So by knowing the equivalent molar conductivity of the electrolyte at infinite dilution, and by knowing the molar conductivity of the electrolyte at a given concentration, it is possible to determine alpha, the degree of dissociation at that particular concentration, that is the ratio of the molar conductivity at the given concentration to the molar conductivity at infinite dilution or zero concentration gives the alpha. It is very easy to say because at the infinite dilution there is a complete dissociation of the electrolyte occurs, so that the number of ions is maximum. All other concentration, only partial ionization occurs, so that the number of ions is accordingly less. So the conducting power is according to that number of ions. So that lambda m at that concentration divided by the lambda m at a limiting concentration or limiting dilution, that is lambda 0 m, that usually gives the measure of the degree of dissociation. So simply you have to remember the degree of dissociation of any electrolyte is the ratio of the molar conductance at a given concentration to the molar conductance at infinite dilution or zero concentration. Okay, this is valid. Only we assume that the speed of the ion does not change with the concentration of the electrolyte. That's an important assumption, but this assumption is now we are going to be immediately, shortly we are going to modify this assumption. This is a wrong assumption. Anyway, you study that. That is, the conducting power of an electrolyte depending on the number of free ions and hence the degree of dissociation. Okay, at any concentration of the electrolyte. Assuming that the speed of the ion does not vary with the concentration of the electrolyte, he said that the degree of dissociation of the electrolyte at any concentration is the ratio of the molar conductance at that concentration, at a given concentration, to its molar conductance at zero concentration or at infinite dilution. Because the fact that at infinite dilution the dissociation of the electrolyte is almost complete, so that it will exhibit its full conducting power. So this is the thing. So next here I have to mention is that means at infinite dilution alpha is almost 1. So at the state of infinite dilution the alpha of almost all the electrolyte become unity. In all other cases it is lesser than unity. Okay. Next assumption, the important factors that affect the degree of dissociation of an electrolyte in their aqueous solution are: 1. The nature of the electrolyte, that I have already mentioned. Strong electrolytes, they are almost fully ionized, weak electrolyte partially ionized. That is the nature of the electrolyte. The nature of the solvent. Aqueous solution like water is with a high dielectric constant favor the dissociation of the electrolyte, and hence a high degree of dissociation. Alpha is much high in the solvent of high dielectric constant like water, acetic acid, alcohol, etc. polar solvent. But in non-polar solvent like benzene, toluene, etc. is very low value. Okay, that is so 1. The nature of the electrolyte, strong and weak electrolyte. Alpha high for very strong and low for weak electrolyte generally at a given concentration. And 2. The nature of the solvent, polar solvent, favor the dissociation. Alpha is high in the polar solvent, but alpha is low in non-polar solvent. The degree of dissociation is not favored. Dissociation of electrolyte is not favored in non-polar solvent with a low dielectric constant. The next, temperature. As the temperature increases, more and more electrolyte get dissociated, so the degree of dissociation increases with the increase of temperature, because ion get free, more energy to get free, and they move. Or dissociation of electrolyte generally increases. Dissociation of electrolyte generally increases, and more ions are produced at high temperature. That is the situation. Okay, I am not going to concern with the speed here now in this theory. And the next important aspect is the dilution or effect of concentration. That is, the degree of dissociation is inversely proportional to concentration or directly proportional to the dilution. As the aqueous solution is diluted, that is the effect of adding more and more water so as to reduce the concentration of electrolyte. That process is called dilution. Or increasing the dilution of electrolyte, more and more electrolyte get dissociated into free ions, so that the number of free ions increases, degree of dissociation increases, and hence the conductivity, molar conductivity increases. So these are the important factors that will affect the degree of the dissociation of the electrolyte. So this theory is called That is considered as the basic concept of theory, that's Arrhenius theory of electrolytic dissociation. But based on this theory, we can look into the conductance behavior of the the two electrolytes. Okay, now we got the limitation. Okay, we have seen that we have two types of electrolyte, that is strong electrolyte and weak electrolyte. Okay, let us explain the behavior of the conductance behavior of the strong and weak electrolyte based on this Arrhenius theory. Then only we find the limit, we are going to get the limitation of the limitation of the theory. The strong electrolyte or those electrolyte which are almost fully dissociated in their initial concentration. That the state, when we prepare a particular electrolyte at a given concentration, that stage is called initial concentration. When a strong electrolyte is prepared at a given concentration, that given concentration, the strong electrolyte is almost fully dissociated. Alpha is almost 1. That is strong electrolyte, and hence they have the very high conducting power. Okay, so that is the strong electrolytes are those electrolytes, they are almost fully dissociated, and alpha is approximately equal to 1. They are fully dissociated into free ions, Okay, and not like to write free ion, they are fully dissociated into ions, so that alpha is exactly almost 1. So they have very high conducting power. Then on increasing the dilution by adding more and more water, there is a gradual increase in their molar conductivity. Okay, there is a gradual increase in their molar conductivity with the dilution. Okay, high value initially. So what is actually happening is that with the increase of dilution, there is a gradual increase like this, and it reaches a limiting value, that is lambda 0, lambda infinity m. So we are plotting lambda m, and this is C and this is V. This is a case of HCl, KCl, etc. Okay, strong electrolyte. Okay, so initially they have high value of conductance because they are almost already fully dissociated. So the number of ions are very high. So the high conductance value, and there is a gradual increase in their conductance with the increase in the dilution, and it reaches a limiting value at infinite dilution. What is happening here? How can you explain? Okay, we'll explain. The case of weak electrolyte. The situation is that they are only purely ionized or feebly or partially ionized, so that the number of ion is low initially. So the conducting power is low. So at a higher concentration, they have initial concentration. The number of ion is low because they are only partially ionized. So the conducting power is low. As we increasing the dilution, there is a sudden increase in their conducting power. And it is going on, increases, the molar conductivity going on, increases with the dilution. That is weak electrolyte. So, based on the Arrhenius theory, how we can explain this behavior? Let me explain this. We can try to explain. That is, according to Arrhenius theory, he said that the speed of the ion is a constant and is not going to be changed. Okay, speed of the ion in a solution is independent of the concentration of solution. The electric conductance of the solution depends only on the number of free ion present in the solution, the number of ion furnished by the electrolyte. So in the case of strong electrolyte, they are almost fully ionized even at the initial concentration. The degree of dissociation is almost 1, and hence they are high conductance essentially. Okay, high conductance value. Then with the increase in the dilution or decrease in the concentration, their conductivity value gradually increases. How? So we cannot explain because there is no ions that is going to be increased here because they are already fully ionized. So with the increase of the dilution, the number of free ion is, there is no further number of free ion is here produced. because the ions are already the electrolyte are almost fully ionized and produce the free ions. And finally it reaches a limiting value. So this variation we cannot explain. Okay, the case of a strong electrolyte. But in the case of weak electrolyte we can explain because they are only purely ionized, so that the conducting power is less or low. As the dilution is increased, more and more electrolyte get dissociated, the degree of dissociation increases and the number of free ion increases tremendously, and at infinite dilution, the almost complete dissociation of the electrolyte occurs, so that it will exhibit full conducting power and going on maximum value. Okay, we can say it like that. So in the case of a weak electrolyte, the Arrhenius theory is almost good, valid, to agree, to explain the conducting behavior. But in the case of a strong electrolyte, we cannot explain the conducting behavior of its conducting behavior because the number of ion is already maximum. It is not going to be increased. So what happened to the theory? There is a limitation of this theory. We cannot explain the conductance behavior of the strong electrolyte with respect to the dilution, with the variation of the increase in the conducting power of a strong electrolyte, we cannot explain by means of the Arrhenius theory. That is the important limitation of the theory. The main limitation arises the fact that he assumed, because he postulated an assumption that is actually wrong. Okay, the assumption, his prediction is wrong. That is, he assumed that the speed of the ion in the aqueous solution does not vary with the concentration of the electron. That is wrong. Okay, that is, the speed of the ion varies with the concentration, because at the initial concentration, when the electrolytes are prepared, the ions are at the close vicinity. The ions are closer together. So the positive and negative ions are in the closer vicinity. They have the electrostatic attractive force. So according to electron, there is an electrostatic interaction. Because of the electrostatic attraction governed by the inverse square law, so which is governed by the inverse square law, there is a force of attraction. F is equal to, okay, that is F is equal to, that is positive ion plus, okay, Q plus into Q minus divided by R square. Okay. So depending, E square by R square, E plus into E minus, E plus into E minus divided by R square. This is the inverse square law. So at the closest distance, the initial concentration, the concentration is Y, there is a very powerful electrostatic attraction between the ions. So the speed of the ion is less because of the electrostatic attraction. So according to, I am going to define what is the speed of the ion. That is another case. That is expressed in terms of a quantity called ionic mobility. The ionic mobility, the speed of the ion is expressed in terms of a quantity called ionic mobility. Ionic mobility, speed of the ion or velocity of the ion, which is defined as the distance travelled by the ion per unit time under an applied potential of 1 volt per square centimeter. So you remember, the distance travelled by a particular ion under a per unit time under a potential of 1 volt per square meter or square meter is called the ionic mobility. So we have U plus and we have U minus. The ionic mobility of the cation and ionic mobility of the anion, which is a function of the electrostatic attraction. So now we are going to modify this. That is, the Arrhenius assumption that the speed of the ion does not vary with the concentration of the electron is wrong. Okay, that is, the speed of the ion changes with the change in the concentration of the electrolyte, or with the increase of the dilution of the electrolyte. The electrostatic force of the attraction diminishes, so that the speed of the ion increases with the dilution. That means, that is why in the case of the strong electrolytes, even though they are fully dissociated, they are not free to move. They are not free to move at the higher concentration. Hence, because of the electrostatic force of attraction. When they are diluted so that the distance between the ion increases, the force of attraction diminishes by the inverse square law. Okay, inverse square law. Therefore, you know that gradually the speed of the ion increases and conducting power increases. And finally, at infinite dilution, when all the ions are free from the electrostatic force of attraction, all the cation and anion are completely free from the electrostatic force of attraction, it will reach a maximum limiting value which can be obtained graphically. Okay, graphically we get the value in the case of a strong electrolyte. But in the case of weak electrolyte, they are only purely ionized, partially ionized, number of ions is less. As the electrolyte is diluted, more and more ion is produced, also the speed of the ion increases, and hence there is a rapid, sudden increase in conductivity, and the going on increases. But the stage of limiting conductivity, lambda infinity m or lambda 0 cannot be determined graphically because it is going on increases. For that, we have to apply, in order to determine lambda 0 m or lambda infinity or m of weak electrolyte, we have to apply a law called Collat's law to determine the degree of dissociation. That's the theoretical work. Okay, so practical, with respect to graphically, we cannot determine the lambda infinity of a weak electrolyte. So that is the conductance behavior, that is the theory, that is the limitation, that is the limitation. So we cannot explain the conductance behavior, the variation of the conductance behavior of a strong electrolyte based on this Arrhenius theory. Okay, it is applicable to weak electrolyte because the weak electrolyte are almost partially ionized and their electrostatic attraction between the ion are only very less compared to the strong electrolyte, and they will obey the Arrhenius theory. And in the case of a weak electrolyte, this is true. So only in the, and again I want to mention is that only in the case of a weak electrolyte, the ratio lambda c by lambda infinity c or lambda infinity is degree of dissociation. So the ratio of lambda c by lambda 0 m, lambda c m by lambda 0 m is alpha, the degree of dissociation, only in the case of weak electrolyte. Okay, only in the case of weak electrolyte, this ratio is equal to the degree of dissociation. But the case of strong electrolyte, this ratio is not its degree of dissociation, but simply its conducting power. That is the situation, that is the fact you have to remember. So in the case of a strong electrolyte, the ratio of the molar conductance at a given concentration to its molar conductance at infinite dilution or zero concentration is not the degree of dissociation, it only is conducting power in the case of a strong electrolyte. And this ratio is equal to degree of dissociation only in the case of weak electrolytes. So that is the limitation of the Arrhenius theory. Thus, we have to modify the Arrhenius theory in order to explain certain behavior, this behavior of a strong electrolyte. So, to explain the conductance behavior of the strong electrolyte, we need a new theory. That theory is actually known as the D by Huckel-Onsager theory. D by Huckel-Onsager theory, we are next going to account that. Before that, let us explain certain other concept here, and also the another. Before that, we have to explain the Collat's law, and also the Oswald dilution law, because the this Oswald dilution law is also applicable only in the case of a weak electrolyte and not in the case of a strong electrolyte. So the limitation of Arrhenius theory is that, one, it is not applicable for a strong electrolyte. We cannot explain the conductance behavior of a strong electrolyte based on the Arrhenius theory. Next, the alpha, the degree of dissociation is equal to, alpha is the degree of dissociation. That is equal to the ratio of lambda c by lambda infinity or lambda 0 only in the case of a weak electrolyte. So it is degree, it is the ratio of the conducting power at a given concentration to conducting power in infinite dilution. That ratio is degree of dissociation only in the case of weak electrolyte. In the case of the strong electrolyte, that ratio is never equal to alpha, the degree of dissociation. Instead, it is called a conducting power of the electrolyte. Okay, it is not degree of dissociation. And next is Next is, this theory could not take into account the variation of the speed of the ion with the dilution, which in turn with depending on the electrostatic force of attraction. That is the main disadvantage of this theory. Arrhenius could not account the variation that occurred in the ionic mobility or speed of the ion due to the electrostatic force of attraction arising from the change in concentration. Thus, the Oswald dilution law, which is applicable only in the case of the strong weak electrolyte, is not applicable in the case of the strong electrolyte. That is equation, that is alpha square C is a constant. K is equal to alpha square C, or alpha is equal to square root of K by C. This row, or alpha is equal to square root of K into V. And this theory is applicable only in the case of a weak electrolyte, and it is not going to be applicable in the case of a strong electrolyte. That's the limitation. Because this theory is entirely based on the Arrhenius theory. Okay? So next class, we have to discuss about the Collat's law. So that I have mentioned, the case of a strong electrolyte, we can determine alpha as suggested by Arrhenius, okay, as the degree of dissociation by knowing lambda C by lambda infinity m. So by measuring lambda infinity m and lambda C conductometrically, and lambda C can be measured conductometrically at a given concentration using a Collat's bridge or meter bridge, Western bridge, and lambda infinity m can be determined graphically in the case of strong electrolyte, and by knowing the ratio we can determine alpha in the case of a strong electrolyte. That is assumed to be, according to Arrhenius, as the degree of dissociation. It is not degree of dissociation. Anyway, graphically we can determine lambda infinity m. So therefore alpha is equal to lambda Cm divided by lambda infinity m. This is determined graphically, so we can obtain alpha. But in the case of weak electrolyte, we cannot determine lambda infinity. We cannot say at what stage lambda infinity is attained. For that, now to get the alpha, the degree of dissociation of a weak electrolyte, we have to determine alpha for the lambda infinity m. That is to be determined theoretically. That is Collat's law. So thank you very much. So next class, I'm going to end up the class today. Next class, I will discuss the Collat's law and then de Broglie theory. Thank you very much for observing this reasoning class.